All right. Good evening to you all. All right. So, we'll look at physics this afternoon, phase 152. All right. So, this aspect of physics we want to look at is called electricity and magnetism. All right. That's the course code for this physics: electricity slash magnetism. Um. Okay, so we are going to take each one after the other. So that's suggests that we are taking electricity first. Okay. Now, today's topic I want to take on electricity is called capacitor. All right, capacitor. So, what is the concept behind capacitor? Capacitor is actually a device. All right, you can write it down that we use in storing electrical charges. All right, capacitor is a device used in storing electrical charges. That is what a capacitor is. All right, so there are different kinds of capacitor. We have mica capacitor, we have paper capacitor, all right, and the other forms. So, um, when you talk about charges, charges is Q, all right. Anywhere in physics, you see we are talking about charge. Charge has a symbol Q, all right. Now, and the rule that governs capacitor is what we call the law of capacitance of a capacitor. So, when you are talking about capacitance, okay, what do we mean, all right? Now, this is the symbol. When you are talking about capacitance, this is symbol of capacitance. So, if I draw this, all right, you call them cells in physics, and the combination of two or more cells is what we call battery. So this is a capacitor, this is a capacitor, this is also a capacitor. Okay, so with this now, when you talk about the capacitance of a capacitor, what is capacitance of a capacitor? So that we can use that particular law to explain what capacitance is. Okay, the law of capacitance of a capacitor actually says that your capacitance is equivalent to the ratio of the charge per potential or per voltage. All right. So charge per potential or charge per voltage is what we call capacitance. So we have the ratio of charge per. So now if you make charge out of the formula, your C is equal to Q over V. All right. So you have C over 1 is equal to Q over V. So you cross multiply. Then you have Q is equal to CV. All right. Charge is equal to CV. Then your capacitance is equal to the charge over potential. So if you are to determine capacitance or charge in a capacitor or capacitor in a capacitor, use the capacitance in farad. Capacitance is measured in farad F, or you can have it in microfarad sometimes. Anyway, here micro means 10 raised to power minus 6. So if I have 1 farad, all right, and I have 1 microfarad will suggest that I have 1 times 10 exponential, 1 times 10 raised to power minus 6. So that's what happens. So your charge is equal to capacitance multiplied by voltage or the potential. Then your capacitance is equal to that charge is equal to capacitance by voltage. Then your capacitance is equal to quantity of charge divided by voltage. Charge is capacitance and voltage. The capacitance is equal to charge divided by voltage. You make series of formula from that end. So, if that is the case, what is my capacitance measured in? If we are to determine the capacitance, all right. Once I say capacitance is defined as the ratio of charge per voltage. Now, your charge is measured in coulomb. All right, this voltage charge is measured in coulomb, and your voltage is measured in volts. All right, so you have capacitance is equal to joule per voltage. All right, that's J V minus 1. All right, coulomb rather V minus 1, CV minus 1. All right, so now that's what we have. So this is coulomb per watt per voltage. All right, that's what we have as the SI unit. Coulomb per voltage is the capacitance, and that coulomb per voltage is also what we call farad. All right, or microfarad. I said microfarad is 10 raised to power minus 6. You can also have picofarad. You can have nanofarad. Nano is minus 9, like so. Q is equal to CV. Now let us see the arrangement of our capacitor. Don't forget that I've mentioned the type of capacitor. We can check other several types of capacitor we have. I said we have paper capacitor, we have mica capacitor. You can check other ones. So now I've mentioned the formulas and the SI unit. So the arrangement of capacitors. Now when you are talking about arrangement of capacitor, all right, your capacitor can be arranged in 2 different ways. All right, so you can either have what we call a series arrangement. You can have a series arrangement and you can have a parallel arrangement. Okay, so these are the 2 ways you can arrange a capacitor. So now when you are talking about a series arrangement, so this is an example of a series arrangement of capacitor. So you have something of this nature. Okay, you have something of this nature. You have one here. All right, so you draw something like this, and like this. So this is what we call a series connection. So C1, C2, C3. Then for parallel, the parallel connection of a capacitance, alright, is like this. So you have something of this nature, you have something of this nature, and you have something of this nature. So you have this, 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 and you have this. This is in series. This C1, this C2, and this C3. This is series, while this is in parallel. Alright, so that is series and parallel connection. So what is the concept behind our series and parallel connection of a capacitor? So let's look at that. So for series connection, alright, now what happened? In series connection, our Q is equal to CV. Alright, we have Q is equal to what? Is equal to CV. And we're using, alright, 3 different capacitors, okay? Or capacitor. So what is going to happen if Q is equal to CV in series? Okay, so let's make capacitance the subject of the formula. So if capacitance is the subject of formula in series, you are going to be having Q is equal to CV. Okay, so you have C is equal to Q over V. Alright, so let's add 3 together. Once you're having 3 different capacitance, so whenever you see C, my C is supposed to be, C total is going to be for 3 capacitance, that is C1 plus C2 plus C3, then to C infinity. Okay, so I have C total is equal to, so anywhere I see CT now, my C total is now going to give us Q over V, then all into total, alright, is equal to, that is C1 plus C2 plus C3 all into C infinity. So my Q over V, alright, then all into, that is V all into total is equal to, anywhere I see C1, I'll now write Q over V. Alright, then I have Q over V1. Okay, then plus anywhere I see C2, I'll write Q over C, Q over V, then I'll put 2 all in that place. Then I have Q over V, I'll put 3 all into that place. Then everything to Q over infinity, plus V all into infinity. That's what we have. Okay, so if this is Q over V, that is in terms of the charge. That is capacitance is equal to that. So you can add them together if you have that total capacitance. So then what's going to be the charge in terms of that? If this is in terms of the capacitance, in terms of the charge, we are going to be having potential. Potential is going to give us Q over C. Alright, if potential is equal to this in terms of the potential, if potential is equal to Q over C, then we have V total is equal to V1 plus V2, alright, plus V3, alright, everything to V infinity. Then our V total is going to give us Q over C. Then everything into total is equal to V1, the same thing, that is Q over C1, everything into total, alright, then plus we have Q over C2, everything into total. Okay, this one is 1, this one is 1, alright, this one is 2, then we have Q over C, this 3, okay, this Q over C3, then everything to Q over C infinity. Okay, now take note in series connection. Take note of that. In series connection, potentials are different, all right, but the currents are the same. Take note of that. In series connection, potentials are different, but but the charge rather are the same. Potential are different, but the charges are the same. So your Vt is equal to V1 because it's different, V2 plus V3 to V infinity. This is series, but your charges are the same. So Q total is equal to Q1 is equal to Q2 is equal to Q3, then it's equal to Q infinity. Alright, everything is to Q infinity. So if that's the case now, if my charges are the same in series connection, if I bring back that formula, what's my formula? My formula was Q over C total, alright, is equal to Q over C1 plus Q over C2 plus Q over C3 all into Q over C infinity. So my charges are the same in series connection. So I'm going to substitute one charges outside. So I have Q, alright, then I'll open a bracket. Now this Q over CT can be written as Q, alright, 1 into CT. You should understand that, alright, because Q times 1 will still give us Q, then over CT. It's equal to, so once Q are the same all true, I can also bring Q, alright, outside. That is over C1 plus 1 over C2 plus 1 over C3, alright, then everything to 1 over C infinity. This one we have, alright. So charges can cancel charges out. So I have Q Q is outside now, so I have 1 over CT, all right, everything into Q is equal to Q open bracket 1 over C1 plus 1 over C2 plus 1 over C3 to 1 over C infinity. Okay, so Q has gone with Q. Then I have 1 over C total is equal to 1 over C1 plus 1 over C2 plus 1 over C3 then to 1 over C infinity. This is what we have as the what, as the parallel connection of a capacitor. Okay, so that is the parallel connection of a capacitor. Then once you are proving the parallel, and the parallel gave us 1 over C total is equal to 1 over C1, all right, plus 1 over C2 plus 1 over C3 all into 1 over C infinity. Then let us move on straight away to our parallel connection. So for the parallel connection, what is going to happen? Don't forget that we said that at series, all right, your potentials are different while currents are the same. So we resorted to 1 over CT in parallel, all right, in series. Sorry, we said in series rather, our potentials are different while what charges are the same. So we resorted to 1 over C1, all right, 1 over C2, 1 over what C3, and to 1 over C infinity. So let's look at the parallel connection now. So for parallel connection, what we have, I told us that our charges, it looks like this. So you have this, you have this, you have this, all right. So you have this, you have this, just a sketch, all right, and you have something of this nature. So this what? This a parallel connection. This C1, this C2, this C3, then the other. So from this place now, what is our Q? Q is equal to what? CV. Okay, now take note, if Q is equal to CV, if I want to add the total charges together like I did in that place, what's going to happen? That is Q total, right? This one is for in terms of the capacitance, but in terms of the charge, what I have what Q total is equal to let's say Q1 plus Q2 plus Q3 then to Q infinity. If I want to add all the charges together, all right, then which is also the same. Once my Q is equal to CV, I can write Q total is equal to Q1, all right, Q is equal to CV. So anywhere I see my Q1, I'll write CV1 plus Q2 will now give me CV2, then Q3 will give me CV3, then everything to CV what? Infinity. So what do I have? Once my Q is equal to CV, so I now have CV, all right, into T. So I have CVT is equal to CV1 plus CV2 plus CV3, then to CV infinity. So I have CV total, okay. My potential, all right, is going to be the same because in parallel connection, charges are different, but potentials are the same. Take note, in parallel connection, charges are different, but potential are the same. In series connection, potential are different, charges are the same. While in parallel connection, charges are different, but potentials are the same. So if potentials are the same, that means that I'm going to be having V total is equal to V1 is equal to V2 is equal to V3, all right, then everything is equal to V infinity. Then anywhere I see V is V. So I'm going to be writing V open bracket C total is equal to everything V there is not different. So I'm going to write C1 plus C2 plus C3, all right, then to C infinity. Then at the end, I have V into CT, all right, V into C1 plus C2 plus C3 to C infinity. Then V has gone with V. So I have CT is equal to C1 plus C2 plus C3, then to C infinity. So this is what we call, this CT is equal to C1 plus C2 plus C3 to C infinity is what we call the connections in what? In a series, in a parallel connection. Alright, this one is in series, while this one is what? Is in parallel.